Alright everyone, welcome back to Cody's Lab. So today I want to attempt to make activated carbon. So this is stuff that you can buy from the store. It's about $6 per 9-ounce little container here. But I want to try making some of my own. So I have here a box of hardwood charcoal. This is just store-bought. I did try making some, but I ended up burning it all up in a failed attempt. Well, at least we know that we can melt stainless steel with a charcoal forge. So, yeah. So this is going to be my starting point. So essentially what this is carbon, a little bit of ash, and it's got a structure which gives it a pretty high surface area. In fact, if you look at it real close, you can see all kinds of little tiny holes and pores, which was originally the vascular structure of the plant. And if you got chemicals that like to stick to carbon, well, that makes a pretty good surface for it to do so. But it could be a lot better. Like this charcoal here still has quite a lot of area where there's just no pores. And also this still contains quite a lot of residual oils and tar, which plug many of the holes. It also makes it so it's hydrophobic and water doesn't like to actually go through this very well. In order to create activated carbon, what we need to do is increase the effective surface area of the charcoal. Now there's many ways to do this. One of them is just get it hotter. If you make the charcoal at a higher temperature, more of those tars will vaporize off and there'll be more pores open. But that's not going to increase it a whole lot. What I'm going to do is react it with superheated steam. So let me explain what that's going to do. So imagine that this piece of clay here is a piece of charcoal, and the tape is some bits of tar. As you can see right here, that piece of tar is covering up one of the pores. Now we can get this hot and drive off the tar. That's pretty simple. Or you could use sodium hydroxide or something to dissolve it off. And now we're left with a piece of carbon with a bunch of little holes in it. Now if we react this with oxygen at high temperatures, you'll burn the charcoal. Oxygen is kind of like a knife. It burns away the carbon pretty indiscriminately. Whatever it touches, it burns off and removes, making the piece of carbon smaller. So what I'm going to do is react the carbon with water instead of air. Now you might be thinking, well, water doesn't react with charcoal. Well, no it doesn't, unless you get it very hot. You know, it takes a lot of activation energy, but water, even at very high temperatures, is more gentle. It's more like taking a stick to it, and it'll pull off little bits. Some parts of the charcoal are more easy to react with than others. There might be catalysts present which help the reaction along, but only in certain places. There might be a piece of ash that the water can't react through. Water can also last long enough that instead of reacting with the first little bit of carbon it runs into, it can actually bounce around and make it down into the pores before reacting. So even the inside of the pores can become more porous. Eventually the piece of carbon will look like a snowflake, fractalized. In fact, it's reasonable to assume that I could increase the surface area by a couple of orders of magnitude. Let's say you accidentally ingest a poison. Well, you'd much rather eat 10 grams of activated carbon than a kilogram of charcoal. Like, this isn't even going to fit in your stomach. So, activated carbon is very useful to have. But I will point out that in a lot of cases, like water purification and stuff, you know, if you just have a barrel of charcoal, that'll work. It'll still clean your water. There's nothing really special about the activated carbon other than you need a smaller mass of it to absorb the same amount. Anyway, let's get to activating it. The first step, of course, is going to be to grind this up into a smaller size. So now that I've got the charcoal crushed, the pieces are all different sorts of sizes. And so I need to classify them down. The pieces that are too big here I can either crush again, or what I'm actually going to do is just throw them over my shoulder into the compost heap. Yeah, that'll turn it into biochar. So the idea here is to get the pieces down as small as I can so that the water vapor, the steam, can penetrate the entire particle. If the particle is too big, only the very outside of it might become activated. So even this stuff here is probably too big for my DIY version, but I am going to save that. And what I'm going to end up with is a bunch of very fine material here, which is mixed with dust. Now, the dust is actually a problem of its own, because if there's too much of it, the particles are all different sizes, then the steam and hot gases might not be able to penetrate it at all, and most of it won't get activated, so it's as if this whole thing is one big piece of charcoal. And so what I'm going to do is scoop it up like this, using this finer screen, finer than this one, and sift out all the dust. And I might use the dust for something else. And now, since the particles are all about the same size, their packing efficiency is decreased, gas can easily pass through them. So I'll just finish this up. So here's my crushed and screened charcoal. All of the pieces should be roughly the same size. So what I'm thinking is I'll have my electric furnace here. It's got coils of wire with electricity running through it that get quite hot. And I'll put the charcoal inside of a stainless steel flask. It's got to be stainless steel because the superheated steam will burn iron if it's unalloyed. And have like a little dish at the bottom, maybe fill this with charcoal here to keep the air out, and then have a stainless steel tube come in, go up to the top, and then maybe have like a tea kettle or something over here to produce the steam. And then of course this will be filled with my crushed charcoal. Let's build it. Okay, so this is what I've come up with. You can see the kettle here. And if I pull the furnace apart, you can see how I did that. I had some spare fire brick, which I just cut to fit everything. And here is the reaction vessel itself. There's another stainless steel dish that goes here. I don't know if you can see down in there. But the tube just bends up and goes into the top of this. To bend this tubing as sharp as I did, I ended up filling it with tin, and that keeps it from collapsing. It wasn't easy to bend, but I was able to do it. So let's just load it up now. I don't want to fill this all the way up. Just do maybe 3/4 of the way full. That should do it. As for the charcoal to remove the oxygen, I'm going to use these large pieces so I don't get them confused. And as for the charcoal that I'm just heating up without the steam, I'm just going to fill up a little soup can here, put it inside of another soup can, add some charcoal around that to keep the oxygen and steam out, and we'll just set that kind of right there so it gets heated the same. And I'll just assemble all this back up and heat it to at least 1700 degrees Fahrenheit. Okay. Crank up the heat. There's the water. Probably don't need that much, but it's gotten a bit dark, but we're finally up to temperature. So I'm gonna heat the kettle just with a blowtorch here. And once it's boiling, I'll close the lid and send some steam into the chamber. Kettle's boiling. I'm gonna put in the steam. Look at that. That's carbon monoxide and hydrogen burning from the steam reacting with the charcoal and producing water gas. Nice, that means it's working. If I remove the steam source, it stops immediately. Okay, so I'm going to do this for a few minutes and then I'll stop and let it heat back up again. This process takes energy, so the charcoal in there is going to be cooling off as I do this. So I can't put the steam in continuously. In fact, I can kind of see it even slowing down a bit. Be a good indicator. Alright, so this is the fourth time I've injected steam. I think I've totaled about 10 minutes worth of steam injection, and this is probably going to be my last time. In fact, I've unplugged the furnace for my light. Now, obviously it would be better if I could stir the charcoal as I'm injecting the steam. But with the way I've got it set up, the rate that I'm injecting the steam is so high and the rate of heating is so slow, the charcoal at the top will react to the steam before the charcoal at the bottom. But as the charcoal reacts to the steam, it cools off because the reaction is endothermic. And the charcoal below that will still be hot, and so the steam will pass through into the still hot charcoal, and it should, in theory, react with the entirety of the mixture. Now, normally I would have taken it off by now because it's probably done, but I'm going to continue injecting this time because I'm going to let it cool off now, and may as well cool it off with the steam. Pro tip if you want your furnace to cool off quickly. Replace the insulating lid with a pan of water. It's finally cooled off, so let's open it up and see what we got. Okay, still got charcoal there. So this should just pretty much have just gotten hot. I don't think any steam would have gotten into there, so that'd be cool. Figure out. I'm gonna take this apart. Okay, board it out. Ooh. I just dumped a bunch out. Here. Fortunately, the size is different, so I'll be able to sort it. That should be our activated charcoal. Hopefully. Let's go test it. So here's our control, the charcoal that has had no treatments done to it. This is the charcoal we've activated, and inside this can should be the charcoal which just got hot. Let me dump out the material that we filled in around the sides, because that might have gotten interacted with steam and air. And now, there's the charcoal, along with some little bits from the can. I might run that through a screen just to pull those out. Okay. Wow, those bits of stuff are, I don't know if you can see that flying around. Now, from just playing with this a little bit, I've noticed that the stuff that I ran the steam through feels slightly denser than the other charcoals. So let's pull out my scale and let's actually have a look at that. Little beaker here. Let's just fill it up with the control to the top so it just kind of shakes off. 19.3 grams. Dump it back out. Let's fill it up with the activated charcoal. Do the same thing. Okay. 23.5. It is heavier, denser. Now I would have thought that it would become less dense, but it kind of makes sense. You know, the charcoal might shrink in size, so now the packing's more efficient. And the ash didn't go anywhere. You know, there's less carbon, but the same amount of ash, and ash is quite heavy. Let's check the stuff that we just got hot. Let's see if the steam had anything to really do with it. Interesting. My guess is the heat must cause the pieces to contract a little bit. That is cool. I didn't know that. Okay, so let's continue with our tests. We need to go get some iodine. So I have here an iodine solution of 31.5 millimolar. So that's about 4 milligrams of iodine per milliliter. And charcoal will absorb the elemental iodine, and the amount that it absorbs should be proportional to the surface area. So what I'm going to do is take a test tube, which I have labeled, kind of hard to see, and I am going to put the test tube on a scale to measure the weight of the test tube, tear that away. I'm going to attempt to put in about a gram of the charcoal. So this is the control, which hasn't had anything done to it. Okay, so now that I've got a gram of the charcoal in the test tube, I'm going to add some hydrochloric acid, approximately 2 milliliters worth, is to make sure that the charcoal is acidified, because the alkaline ash in the charcoal will react with the iodine. Let me get this acidified. I might even warm it up with a torch a little bit just to make sure it reacts. Now that I have the charcoal acidified, I'm going to add 25 milliliters of the iodine solution. This is iodine and alcohol, by the way. Hopefully this fits. Oh, perfect. Okay. I'm going to have to find a cap for this. So here's all my samples. I'll just kind of give these a shake every now and then. Okay, so it's the next day. These have sit for about 12 hours. And you can already see that the activated carbon test tubes are significantly lighter than the non-activated carbon test tubes. This would indicate that they have absorbed significantly more iodine. And in fact, my activated carbon appears even lighter than the commercially activated carbon, which would indicate mine's better. But to get some actual numbers, I have set up a burette and a sodium thiosulfate solution, which is 31.5 millimolar, just like my iodine solution was. And before you ask, it did occur to me that since I added 2 milliliters of hydrochloric acid each vial, it diluted the solution slightly, so I will need less of the thiosulfate to neutralize the iodine. But what I'm going to do is transfer 10 milliliters of the iodine solution into this little beaker, and then I'm going to fill the burette with the thiosulfate, and we're going to titrate and see just how much iodine was absorbed from the solution. So let's start with my activated carbon. Okay, and now I'm going to run a cotton ball down its throat in order to filter out any charcoal that's floating around in the solution. That could mess with my results. Let's push that down to the bottom. Oh, no. Might have to pull some out first. I'll use a pipette to transfer it. Okay, there's my 10 milliliters. I'm going to transfer this over to here. Rinse it with a bit of water. Concentration here doesn't matter, it's the amount of iodine in 10 milliliters, so I need to make sure I have the 10 milliliters of the iodine solution. Okay, the burette is full. Let's put that under it. Begin the titration. Just let it out a little at a time, give it a stir. Oh, there's a bubble. No, 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 no. Okay, crisis averted. Doing this pretty much just dropwise until the solution goes clear. Ooh, it's almost clear now. There it is. That took 0.7 milliliters of the thiosulfate solution. So I just wrote down that result here, and I guess it's time to work on the other three. So here are my results. The control, the original charcoal, was able to absorb only 2 milligrams of iodine per gram. The stuff that we heated up managed to absorb 30 milligrams per gram, which is quite a lot actually. That's a pretty substantial jump there. The stuff that I activated with steam managed to absorb 92.5 milligrams per gram. Is more than the stuff that we just heated up, so the steam definitely helped. And the commercial activated carbon absorbed 89 milligrams per gram. Now keep in mind there's probably pretty big error bars on these numbers, but it still shows that I definitely was able to activate it, and to a level comparable to what is commercially available. So there you have it. You now know how to make activated carbon. So if you're wondering what my yield was, this is about 2 ounces. I lost a bunch of it. I'm sure I could do better, but considering I only used about 2 kilowatt hours worth of electricity, it's still cost effective as long as I can do multiple batches. I attempted to make some using a more primitive method, you know, not using an electric kiln. That failed, but I'll still upload the video probably to the second channel. If you guys want to go check that out, feel free. And also, speaking of charcoal, I finally got back together with Good and Basic, and we burned a whole lot of it to smelt Utah bog iron. So if you guys want to check that out, I'll leave a link for that as well. So, hope you enjoyed. I'll see you next time.